Hey guys, our last video in this unit is solution stoichiometry. So we're going to take everything we've learned so far and apply it. So we're going to take our initial stoichiometry from the previous unit and we're going to bring in concentrations. Okay, so we are going to, at the end of this video, perform solution stoichiometry problems. So instead of using a pure liquid, now we're going to be able to use a mixture and we're going to be able to perform and interpret titration data. So when we are talking about adding in concentration, now we can directly take our volume of a solution. We can use the molarity to go directly from liters into moles. So it's actually a simplification of stoichiometry. We don't have to look at molar masses. If we already have our concentration, we just take our concentration, multiply it by our liters. That'll cancel out liters, give us moles of our solute. So we've brought in a last portion of our stoichiometry roadmap until we get to our very last unit. Okay, let's go ahead and try an example. So we've got the following problem. We've got grams of calcium hydroxide. We want to know how many that are needed to neutralize 25 milliliters of nitric acid. Anytime we see something like this, we know this is a stoichiometry problem, right? It's asking for how much of one thing for another thing. So we need to first have a balanced equation. So we've got our calcium hydroxide reacting with our nitric acid. And this is a hydroxide base, so we're going to produce water and a salt. And we need to know our charges. So make sure you're able to come up with the charges. Calcium is 2 plus, nitrite is -1. So we need 2 nitrite ions to balance out the 2 plus charge of the calcium. So we produce calcium nitrate, which has 2 nitrate ions. Next thing we want to do is balance this out like so. And now we have our balanced equation and we can move on to the next step. So it wants to know grams of calcium hydroxide. So this is the desired thing. This is what we want to know. This is what we do know, 25 milliliters of 0.1 molar nitric acid. From concentration and volume, we can get moles of nitric acid, and once we have moles of nitric acid, we can go into moles of calcium hydroxide, and from moles of calcium hydroxide, we can go into grams of calcium hydroxide. So we're going to take our 25.0 milliliters and convert this into liters so we can use our concentration. And we get 0.0250 liters. And then we can multiply this by our concentration, 0.100 moles of our nitric acid per liter, canceling out our liters, and giving us 0.00250 moles of nitric acid. And then from there, we can convert from moles of nitric acid into moles of calcium hydroxide using our balance equation. So we have 0.00250 moles of nitric acid. For every 2 moles of nitric acid, we neutralize 1 mole of calcium hydroxide, giving us 0.00125 moles of calcium hydroxide. And then we can convert that into grams using our molar mass of calcium hydroxide, which is 74.093 grams per 1 mole of calcium hydroxide. So we, at the end, have 0.926 grams of calcium hydroxide. So in order to neutralize 25 milliliters of 0.1 molar nitric acid, we need 0.926 grams of calcium hydroxide. So titrations, our next thing, is like taking solution stoichiometry, adding in acid-base chemistry, and giving us a problem that is a lot of fun to solve. So neutralization titration is a titration of neutralization reaction. So we have to have a neutralization reaction. This is not the only type of titration we can do. I'm going to show a kind of example of another one at the end of this lecture, but a neutralization titration makes use of a neutralization reaction. Okay, so it is a technique that's used in order to determine the concentration of a solute using the solution that has a known concentration or a standard solution, stock solution, something like that. A technique used in order to determine the concentration of an unknown using a solution with a known concentration. So in the case of an acid-base titration, one of them, the acid or the base, will have an unknown concentration, and then the other one, the one that you're going to react it with, is going to have a known concentration. So it's going to be a stock solution, or we also in titration call this a standard solution. So we're going to use a standard solution, react it with the unknown to find out what the concentration of the unknown is. So our standard solution is added until the two substances are stoichiometrically equivalent. So our standard solution is added to the unknown solution until the two are stoichiometrically equivalent. And there's going to be some sort of indicator that will tell you when they are stoichiometrically equivalent. Over to the right, you see what a titration setup looks like. You've got a burette, and in that burette, you have your titrant. So in the burette is the titrant. Then below that, usually in a conical flask or Erlenmeyer flask, you have your unknown or your analyte. So in a Erlenmeyer flask is the unknown, which is the analyte. So the titrant is the same as a standard solution. So you're going to add your standard solution in with the burette until your unknown, your analyte, is fully reacted. The titrant is added to the analyte until the analyte is fully reacted. Okay? So when they are stoichiometrically equivalent. In the case of an acid-base neutralization, generally what we have is H plus OH minus going to H2O. Not always, but most of them. When these are equal to each other, we are stoichiometrically equivalent, and we've reached our endpoint of our reaction, or our titrant, or of our titration. Okay? So you'll keep adding in one of them until you reach this point which is a pH equal to 7. So at the end of an acid-base neutralization titration, if we have a strong acid and strong base, our pH will be 7. We can either indicate that using an indicator. So we have an indicator, which changes colors at the neutralization pH. So it'll turn pink, for instance, once we've reached neutralization. Or you can look at use a pH probe to see when you're at a pH of 7. Either one of those will tell you that you've reached the point where you're at stoichiometrically equivalent amounts of acid and base, so you can stop the reaction. Okay. So with a titration, generally what you're going to be looking at is volume of titrant added and pH. So during a titration, you look at volume of titrant added and pH. Okay. You will add in amounts of titrant, and then you'll take the pH. And what you can develop is what's called a titration curve. So it is pH versus volume of your titrant. So, or volume of titrant versus pH of your analyte solution. So if you have, in this case, this is a base titrant and an acid analyte. So we start out at a very, very acidic pH, very, very low pH. And as we add in our titrant, the pH is going to increase until we reach what's called the equivalence point. So the equivalence point is when our H plus ion concentration is equal to our OH minus ion concentration, and we have reached our end point. So this is when we're stoichiometrically equivalent between the two. A lot of times you will continue beyond there to see a full titration curve. So you won't stop just here. You'll want to actually see this whole funky curve. If we have the opposite, if we have a base analyte and a acid titrant, it's going to just look the opposite, right? So it's going to start out basic, go down, and still at a pH equal to 7, we'll have that equivalence point where we've neutralized everything, where everything is stoichiometrically equivalent. Our moles of acid, our moles of base are equal to each other if we are talking about a monoprotic acid, so one proton, a monobasic base, one hydroxide. It will look different if we do not have monoprotic and monobasic. Okay, so we can determine concentration data from our titration data. What we're going to do is basically you're trying to find your volume of your standard solution needed in order to reach your equivalence point. So that's why we look at volume of titrant versus our pH of our analyte. So once you get that volume of equivalence, the volume of titrant at equivalence, you can use the molarity of your standard solution to get your moles of your titrant. Then using your stoichiometric coefficients from your balanced equation, you can get your moles of your solute, your moles of your analyte, and then using the volume of the analyte, you can find your molarity of your analyte. Now, keep in mind, again, monobasic base, monoprotic acid, this is how this is going to behave. It's going to be very simple. But once we go into diprotic acids or dibasic bases, it becomes much more complicated because you have to take into account that these are no longer one-to-one mole ratios. So let's try a diprotic acid so I can show you exactly what I mean. So we've got sulfuric acid and sodium hydroxide. Before we do anything else, let's go ahead and write out our neutralization there. So we have H2SO4 plus NaOH goes to Na2SO4 plus water, like so. Now, once we have this, we can go ahead and read what our problem actually says. So titration reveals that 11.6 milliliters of 3 molar sulfuric acid is required to fully neutralize 25 milliliters of sodium hydroxide. So we have a volume and a concentration. We know that this is our titrant or our standard solution. So titrant. As such, this must be our analyte. So we're going to start out with our titrant, figure out how many moles of our titrant we have. We have 11.6 milliliters of sulfuric acid. We need to convert that into liters, giving us 0.0116 liters of sulfuric acid. And now we can use our concentration, 3.0 molar, canceling out our liters, leaving us with moles. This gives us 0.035 moles of sulfuric acid. And now we can use our balance equation to go from moles of sulfuric acid into moles of our analyte. So for every 1 mole of sulfuric acid, we neutralize 2 moles of sodium hydroxide, giving us 0.070 moles of sodium hydroxide. Now, we have our moles of sodium hydroxide. We want concentration, so we're going to look back at our problem where it says we have 25.00 milliliters of sodium hydroxide. So this is our volume, this is our moles. We're just going to divide it out. So we have 0.070 moles of sodium hydroxide. Divide this by 25.00 milliliters, and then convert this into liters, giving us 2.8 molar sodium hydroxide. So from our titrant, we were able to solve for our concentration of our analyte. That's usually what we're trying to do. There are titration problems that are going to be a little different. They're not necessarily going to be acid-base neutralization reactions, but they're going to be a reaction that has an endpoint that we can solve for. So first up, we've got a stoichiometry / titration problem. So we need to know what our balanced equation is. So silver nitrate is going to react with chlorine ions. And when that occurs, we produce silver chloride and nitrate ions. Now, silver nitrate is aqueous, chlorine ions are aqueous, but silver chloride is a precipitate, and nitrate is going to be, again, an ion that's in solutions. We have our titrant. Let's go ahead and convert that into moles of titrant. We have 20.2 milliliters of our silver nitrate. We're going to convert that into liters. And then we're going to multiply that by our molarity, giving us 0.00202 moles of silver nitrate. And then we could take our 0.00202 moles of silver nitrate, convert that into moles of chlorine, 1 mole of Cl- for every 1 mole of silver nitrate, gives us 0.00202 moles of chlorine ions, and then using our molar mass of atomic chlorine, 35.453 grams per 1 mole of chlorine, we can solve for our moles, giving us 0.0716 grams of chlorine ions. That's everything. So I hope you guys know a little bit more about solution stoichiometry and titrations, and I will talk to you guys in the next unit.